something of the order of millions of stars. About 100,000 of those are going to be stars that are our targets. But when we look at this image, what's special about it is there are no blank spaces. All the detectors are working and working well. So that was a wonderful result. What we've focused in here is on a star that's known to have a planet. This planet was detected from the ground a couple of years ago. The star name is HAT P7, and it's a Jovian-like planet that orbits it in a very short period of orbit. To make the measurements, to find Earth, what we're talking about is doing transfer photometry. Basically, when a Jupiter moves in front of a star, it blocks some light, about 1%. And that's what we'll see here. But what we're talking about with this mission is the precision required to find 1/100th of that, 1% of 1%, about 100 parts per million. And so to do that, to have the precision to find Earth, you have to be in space. Because on Earth, you look through the Earth's atmosphere with the dust, the clouds, the day-night cycle. So let's compare what the discovery figure for HAT P7b, B is the name of the planet, with what Kepler did during a few days in his calibration cycle. So could I have this first still? In this figure at the top, what we're talking about is the brightness, the change of brightness of the star, and the horizontal axis is time. And what we see at the top is a lot of points scattered a great deal because of the Earth's atmosphere, but we can see there is a dip there. That dip is the dip of a Jovian planet, actually bigger than Jupiter, transiting its star. Below it is the same star, the same planet measured by Kepler. And it doesn't have all that scatter. All instruments have noise, but the noise for Kepler is 100 times smaller. So it's actually contained within the width of that line. It's that much better. It has the precision necessary. So let's go to the next magnification of the Kepler measurement. We're going to magnify it by a factor of 7 at the top. And what we see here is now that little dip is a very large dip. It dominates the figure. But what's most important here is if we look at that curve to the upper right, what we see is there's another very small dip. That's the size of a dip that would come about if you had an Earth-sized transit. That's what we're looking for. That's the precision that we need. The bottom figure is, again, the same data, but now it's got a magnification of 100. Here the transit is so big it simply goes off scale. But what we see now instead is a level curve between the two transits. We see a rise in that light, and then a dip, and another rise. We see the scatter. There is scatter in this mission, with this instrument, but it's sufficient to find that dip. That little dip is about 120 parts per million, and we could readily find something half that big. We could readily find an Earth-sized planet. So this proves we can find Earth-sized planets with this mission, with this photometer. The other thing that we have found here is the fact that that light rises with time. That rise in the amount of light is not light from the star. This is light from the planet. We are actually seeing light from the star itself. And we're seeing that disappear as the planet goes behind the star and gets occulted. So we see two things here. We see the instrument has the precision to find Earth-sized planets, and we're seeing a new discovery. The first time anyone has ever seen light from this planet, and we can use that light to understand the physics of that atmosphere, and we'll talk about that a little bit later. What I'd like to do is illustrate these points with an animation. So could I have the next animation? In this animation, we have an artist's concept of a star and a planet orbiting it. We see as the planet orbits the star, it undergoes phases. Phases just like the moon. When it's pointed at the star and we're seeing the back side, it's dark. When we're seeing the front side, we're seeing light reflected from the planet, but most of all, we're seeing light emitted by the planet. It is so hot, it emits an enormous amount of light in that particular atmosphere. And below to the right, we're actually seeing the light curve. When the planet goes around behind, you see there's this little dip because the light from the planet's gone. Then you see come back around. The phase is such that we see the backside, and again, the amplitude is very low. This planet orbits some 22 times closer to its star than Earth does to the sun. It's about 2,700 degrees Kelvin. It's so hot it actually glows. It looks like the heating element in your toaster or your stove. In fact, if you were to back away from the star system a bit and look at it, what you would see is the star, and you see what would look like a glowing ember from a campfire floating in the sky, orbiting that star. It's that hot. Now, clearly, what we've talked about is precision. We've talked about this discovery. We need to talk about really the answers to your question, and that will be, well, if we've got the precision, we're looking at over 100,000 stars, what are we finding right now? And the answer is, the system is working well. We're finding hundreds of interesting events. But most of those events are eclipsing binaries, or they're spots on stars. They're astrophysical phenomena that aren't transits. So we have to distinguish between the two before we can announce a discovery. So as part of that, we have a ground-based program that's running where we're using the Keck telescope in Hawaii, we're using the HET in Texas, we're using the WIND telescope in Arizona, the Nordic Optical Telescope in the Canary Islands. All of these are following up on these interesting signals to see if they're eclipsing binaries or some other false positive, or are they planets. If we think they're planets, we still have work to do before we make an announcement. We have to find out what is the size of the star, because the transit tells you how big the planet is relative to the star. So we've got our co-investigators doing the work to determine the size of these stars. And we expect to finish all this work, see 3 transits. We need a minimum of 3 transits to make sure it's not spots on a star, and make announcements early next year with the short period planets. But when it comes to finding Earth in Earth's orbit, we need to find those 3 transits, each one of which is separated by a year. So we're expecting it's going to be 3 years before we get those 3 transits, although for all we know, we already have one of the transits in already. We've got to do that. We've got to follow up with telescopes, and it's very difficult to do small planets like the Earth. And so it's going to be 2012 before we can tell you whether lots of Earths are as common in our galaxy, or are we alone. In the meantime, while we wait, we can talk about the physics of the atmosphere of the planet that we've made the measurement of. And Sarah's an expert in understanding these atmospheres. Sarah?
Thank you, Bill. This is a very exciting time for exoplanets. We're able to ask and begin to answer a lot of interesting questions about hot Jupiters and other exoplanets. Can I have the animation, please? Some of the questions are, what are planets made of? What chemicals are in their atmospheres? And how do exoplanets compare to Jupiter? This animation is an artist's conception of a flyby of an exoplanet. The exoplanet looks a lot like Jupiter. It's got a couple of moons. And we can't send spacecraft to exoplanets. They're too far away. But we are using space telescopes like Spitzer and Hubble and now Kepler to observe exoplanets from far away and to learn about their atmospheres. What I'm going to do next is go into some detail about the HAT P7b exoplanet. Can I have the next animation, please? And we're going to return to the animation that Bill already spoke to, which shows the artist's conception of the planet orbiting the star, where the hot face of the planet comes in and out of Kepler's view. And I just want to emphasize again, the picture at the bottom of the animation is showing the light in the combined light of the planet and star. We can't spatially separate the planet and star on the sky, but Kepler is looking at the light all mixed together. I also want to add a second time and re-emphasize that this planet, HAT P7b, was already known. It was known before Kepler's launch. And what is new is the secondary eclipse, the little drop of light that tells us something about the temperature of the planet, and the phase curve, the rise and fall of light, showing that the planet is hotter on one side than the other. This curve immediately tells us that this planet is really not like Jupiter at all. It is, let's think about Jupiter and Earth, for example, would just have a straight line. They wouldn't show a curve like that. Let's think about Earth for a minute and the hottest place on Earth today. It kind of feels like it's the hottest place in Washington. but actually it's in Central Africa.